Let me explain PCA as well as the math behind it. Principal component analysis is best understood in the context of classification problem. Let's say we have a bunch of data points and each data point has 3 numbers attached to it. For example, they may be height, circumference, and weight. And the goal is to be able to classify the object as red or green depending on the numbers. Usually you're given some examples that are already classified for you, like this one, and from that you want to come up with a way to automatically classify any new data points you get. Now, if the data point is projected on the xy plane, you see that some of the regions of red and green overlap, like right here. That is not so good because we're trying to classify things. However, if you look at this 3D scatter plot, and if you rotate it around, you see that there are some directions where you project, you get lots of overlap, but there are also some directions when you project, there's not much overlap. And this is the idea of the principal component analysis. It's about finding these directions that enable you to classify a higher dimension data by projecting onto lower dimensions. And then as an example, here if we have the correct axis, the first principal component axis and the second principal direction, if these 2 directions are chosen wisely, then the projection has clear distinction between the red and the green. Now you can even go lower. Here's the data projected onto the x-axis only, and this shows that just using the x coordinates is not good for classification because there are overlaps here. But if you used the principal direction, which in this picture is something like this, from going from here to there, then there is a clear boundary so that you can easily classify between the red and the green. Of course, this example is overly optimistic, and in many cases the 2 categories will still overlap and you may need to use more directions to distinguish them. However, it is usually the case that you can project the data to a lower dimension and still be able to classify the data in the projection if you use PCA. This reduces the number of parameters to be considered for a given data to be classified, and in the reduced dimension, the classification algorithm becomes faster. Sometimes it gains accuracy as well. The idea behind PCA is this: the best direction to project the data onto is the direction that the data is spread out the most. But how do we measure spread out? For that, we need to know the concept of variation. For a data of n real values x1, x2 through xn, the average is the sum divided by n, and we denote it as E of x or x bar. The variance of the data is defined as the square sum of the difference between each points and the average, and you divide it by n. Now, there is an important identity we will need for the variance, which is that the variance of x is E of x squared minus square of E of x. In other words, variance is equal to average of the square minus square of the average. Here's a proof of this identity, which is quite elementary, but I do not want to spend time on this. If you're curious to know, you can stop the video and read the proof. Here's another proof that's somewhat simpler because we're using the property of E of x, and you can also stop the video if you're interested in learning the proof. We also need to know the concept of covariance. For a data of 2-dimensional vectors of size n, say x1, y1, x2, y2 through xn, yn, covariance of xy is defined as 1 over n times the sum of x minus the average of x, y minus the average of y, and there is an identity for covariance as well. Covariance of xy is E of xy minus E of x times E of y. Now notice that the variance of x is covariance of x and x, and if you take the covariance identity and replace y by x, you get the variance identity we had previously. So the identity for variance is a special case of this one. Another important fact about covariance is that it is symmetric, meaning that covariance of xy is same as covariance of yx. This can easily be seen from the definition of covariance here. Here is what we want to do. We want to find the best direction for classifying two-dimensional data points. Here we have 50 green points and 50 red points. We want to find the best axis to project the data. You can see by intuition that this direction given by the blue unit vector should be it. If you project the entire data set onto this axis given by the blue arrow, you have the most widely spread projection with the smallest overlapping region relative to the size of the spread. But how do we find it using math? Well, to do that, you need to know the formula for projection. Suppose u hat is equal to AB, and it's a unit vector, meaning that the size is 1. A squared plus b squared should equal to 1 if it's a unit vector. For such a unit vector, the projection of a vector v xi yi onto the unit vector u hat is projection of u hat v equals to v dot u hat, where this dot is the dot product between the vectors, and the dot product is computed by axi plus byi. Graphically, this is the projection. Here's the vector v, here's the blue arrow unit vector u, and the projection of v onto u is this orange line. It's actually this length, and another name for this projection is called the component. Now, since xy projected onto AB is ax plus by, and since we want to find the direction u such that the variance of the projection is maximized, we can reformulate the question as finding the unit vector u hat such that the variance of ax plus by is maximized. Now, we can calculate the variance of ax plus by to get this expression here, which in turn can be written in a matrix form. The matrix in the middle, which is made up of covariance of x and x, xy, yx, and yy, is called the covariance matrix. We see that this is symmetric because if you take the transpose of this matrix, these diagonals stay, and this one becomes that, this one becomes that, and since covariance of xy is same as covariance of yx, this matrix is indeed symmetric. If we have a symmetric matrix, we then need the help of a theorem called Spectral theorem for symmetric matrices. This is rather a hard theorem that you learn after one semester of linear algebra, so let me just make the statement here. The statement is that any real symmetric matrix has orthonormal bases of eigenvectors. The implication of this is that any real symmetric matrix can be diagonalized by a real orthonormal matrix. More specifically, let's say Mn and Pq are orthonormal eigenvectors of x, y, y, z. This is symmetric, and the statement here guarantees that such two orthonormal eigenvectors exist with eigenvalues lambda 1 and lambda 2. We're going to assume that lambda 1 is greater than lambda 2 in the following discussion. Now, if we simply use the definition of eigenvectors, if you multiply this matrix to Mn, lambda 1 will appear because lambda 1 is the eigenvalue for the eigenvector Mn, and lambda 2 will appear here because it's the eigenvalue for the eigenvector Pq. Then we can rewrite this as MPNQ times this diagonal matrix of diagonal lambda 1, lambda 2. And now all you have to do is multiply the inverse of this to the other side. So now we have expressed the given matrix, given symmetric matrix, as a diagonalization conjugated by these two orthonormal matrices. I haven't explained what orthonormal matrices is, but I'm going to explain a little later. For now, for the moment being, I'll just say that orthonormal matrices are matrices such that the inverse is same as its transpose. So if you take this matrix and transpose it, this becomes the inverse. Oh, we have done so much math, I think we need to recap for a minute. So far, this is what we have. We figured out that variation of ax plus by is this expression here, where the middle one, being symmetric, can be expressed as this diagonalized version. And we want to find the unit vector AB that will maximize this expression. To go further, we still have to talk about orthonormal matrices. The columns of MP and Q, which are MN and PQ, are orthonormal. This means that ortho means that they are perpendicular, so that if you take the dot product of the two, MP plus NQ, you get 0. And also the normal part means that each vector is normalized. In other words, they are size 1. So that m squared plus n squared will be 1 and p squared plus q squared will be 1. This immediately says that if you multiply the transpose of this matrix to itself, and by straightforward calculation, you get the identity matrix 1, 0, 0, 1. That means that the transpose is inverse of this matrix. And that's what orthonormal matrices are. Orthonormal matrices have two definitions. One is it's a matrix whose transpose is its inverse. Another is that all the column vectors form orthonormal basis for the given vector space. Now, when this happens, you can also see that the rows are orthonormal as well. In other words, if you do m squared plus p squared, it's 1. If you do n squared plus q squared, it's 1. And also these two vectors, if you do the dot product, you get 0. Graphically, this also has the meaning of rotation. If you take the orthonormal matrix MP and Q and multiply it to any vector AB, it has the effect of rotating by this amount shown in yellow. You can see that if you multiply 0, 1 to MP and Q, you get P comma Q. And if you multiply 1, 0 to MP and Q, you get M comma N. And since this orthonormal basis is rotated to this orthonormal basis, we do see that this matrix multiplication must be a rotation. Okay, now back to what we are trying to do. We want to maximize this, but we know quite a bit about this matrix. Now we know that this matrix times AB is just the rotation of a unit vector, and since rotating a unit vector to a matrix still preserves its size, in other words, still a unit vector, we can name it as A star B star. And if you do that, then you can see that this part will be the row vector A star B star, and the above expression now becomes simply lambda 1 A star squared plus lambda 2 B star squared. With still the condition is that A star comma B star is a unit vector. In other words, they squared to add to 1. This has the maximum value of lambda when A star is 1 and B star is 0. Remember, lambda 1 is greater than lambda 2. That was our assumption. So this expression can only be maximized when this is 1 and that's 0, if you have this condition. So here we have the conclusion. You can check that if you set A, B as Mn, if you plug it in, you see that Mn times Mn gives you 1, PQ times AB, well, PQ times Mn gives you 0. So you do get 1, 0 for A star, B star as what we required. And that tells us that the principal direction is the eigenvector direction with the highest eigenvalue lambda 1. Here I'm assuming that Mn is a unit vector, which is also an eigenvector of the covariance matrix. Now let me give you some definitions. The Mn is the first principal direction, also known as first principal axis. And for any data point xi, yi, the first principal component will be xi, yi dotted with mn, which is xim plus yin. This can be done similarly in higher dimensions. So for example, if we had a data set with 3 components, for a data set of 3-dimensional vectors of size n, then we can compute the covariance matrix as here. And notice that this time it's 3 by 3 matrix because we have 3 variables x, y, and z. And the unit vector ABC, direction that maximizes the variance of ax plus by plus cz, is the eigenvector of the above covariance matrix with the highest eigenvalue. That is the first principal direction of this data set. So this unit vector is determined by the data set through the covariance matrix. You first have to calculate the covariance matrix, and then you can figure out the eigenvectors. It's a symmetric matrix as before, so it should have an eigenvector with the highest eigenvalue, and the highest eigenvalue one, that eigenvector is the first principal direction. Now, you can get the covariance matrix from the data matrix, or you can also do the PCA straight from the data matrix. And we first assume that you have the data points x1, y1, z1, x2, y2, z2 through xn, yn, zn, has the property that all mean values are 0. If not, one can calculate the mean and subtract the mean. In other words, you can calculate the x bar, the mean of x1, x2 through xn, subtract that from all the x1, x2, and xn, calculate the y bar, calculate the z bar, and subtract it from each of these. Now, if we assume that, then the variance can easily be calculated now as the square sum of the data points divided by n. We don't have to subtract the mean value anymore because the mean value is 0. And likewise, the covariance is much simpler. It's just 1 over n times the product of the x and y values, and so on. If we put S as the data matrix, which is x1, y1, z1 becoming the first row, x2, y2, z2 becoming the second row, all the way up to xn, yn, zn, then you can see that because of the relationship that we figured out here, the covariance matrix is equal to 1 over n times S transpose S. In other words, it's 1 over n times the product of the transposed matrix with itself. Now I have to quote another important theorem from linear algebra, the singular value decomposition. And I have a separate video on this, so if you're interested, you should watch the video, and I'll put the link in the description of this video. Now, the singular value decomposition says this: any real matrix S can be written as S equals to UD VT, where UV are orthogonal matrices and D is a diagonal matrix. And the D has the diagonal elements that are called the singular values of S. Now, we found out in the previous slide that the C equals to 1 over n STS is the covariance matrix, then if we plug in the SVD, the singular value decomposition from above, we see that C is equal to V times 1 over n dTd Vt. And notice that this is diagonal, this is diagonal. If you multiply two diagonal matrices, you get diagonal, and dividing by a scalar is still diagonal. So this is diagonal, and you have V and Vt conjugate. These are both orthogonal. So we see that this is exactly the orthonormal matrix that diagonalized the covariance matrix. So we see that the columns of V are the principal directions. Moreover, you'll see that the principal components are the columns of UD. So now let me explain PCA in general dimensions. In general, if n data points of k dimensions is given, make a matrix of n number of k-dimensional row vectors, call it S. Just like before, we just put the data as rows. You make this matrix S. And if you do the singular value decomposition of S as UDVT, we get the principal direction as the columns of V. Moreover, the columns of V are eigenvectors of STS, and we may order the columns so that the eigenvectors with higher eigenvalues appear first. In such a case, the first column is the first principal direction, second column is the second principal direction, and so on. For any point, to get the first principal component, one only has to do a dot product, which is the projection, with the first principal direction. Okay, I hope this clarified all the math involved in PCA. Though I haven't explained all the math, please do watch the other video explaining singular value decomposition and you will know everything. Thanks for watching. Please go to my website posted in the video description to find the list of all the videos I've made on my channel. Thank you.